All right, we're going to try doing another one of these problems again. Again, the goal of this series is to give you confidence both in how to prepare for these types of problems, as well as to give you an idea of how to present your knowledge, present your experience, present who you are as a programmer during the interview. So it's really trying to do two things. In other words, my claim is that the way that you should be doing these sorts of problems is independent of whether or not someone's watching you. You don't want to just write code. That's not prepping for these interviews. You've been writing code. That's your job, is writing code. You need to write code in a particular way so that the interviewer and you can have a conversation, an ongoing conversation throughout the whole interview. You don't want your interviewer to get bored. You want them to stay engaged. You are doing a different thing than your job. There is real value in these interviews, even though honestly it feels like there isn't. They feel gross. I get it. They feel like you're trying to do what comes natural to you in a very unnatural way. But the point of these is to have this communication, to have this conversation. And it's just very unique to our profession that these kinds of conversations are even possible. All right, so the first thing is we're going to dive into this problem. Again, I'm just adapting something from LeetCode. I think what they're doing is wonderful. I'm not trying to in any way take away from what LeetCode's doing. The reason I'm not using their interface directly, even though a lot of people will interview you in those interfaces, is that I feel like you can get a lot of experience just functioning inside of LeetCode. The thing that becomes sort of scary is when you're using your environment in a natural or in an unnatural way during the interview. So that's why I'm sort of pulling it out of LeetCode, transforming it a little bit. This is the way I've experienced a lot more interviews personally, and I feel like this is the way to sort of better prepare for those kinds of interviews rather than doing something that feels very gamified. It's just my personal preference and the way I wanted to share my thoughts on these interview problems. All right, so let's dive into this problem. So in this one, the name of it from LeetCode is populating next-right pointers in each node. So we're going to be given a node definition, so we're given a class below. And then we'll also be given a root node of a binary tree. So remember, binary trees, they are a data structure that allows you to have a left and a right. This particular binary tree, we're going to be given a root node to that. So we're going to be given a parent with a left and right child. And every node in this binary tree, it's either going to have both of its child nodes empty, so it's a leaf, or both of its child nodes will be populated. So this means every node is either a binary, a fork, or a leaf. And so this is a perfectly balanced tree, a perfectly populated tree. So we're going to be given this perfect binary tree, and then we're going to set the value of next. So there's an additional pointer that's not in normal binary trees. This additional pointer is called next, and the point of this next pointer is to point to the next right node in the same level of the tree. But if a node is at the rightmost, so if it's at the end of its level, then we're going to set that pointer to null. So given this perfect binary tree, we want to take the 1 and point it to null. There is no next at the root node. We want to take 2, point it to 3, because the left pointer should point to the right pointer. But then the 3 is going to point to null, again, because it's the right on its node. 4 goes to 5. Again, left points to right. That makes sense. 5 is pointing at 6. So the right node from the 2 child is pointing to the left node from the 3 child. All right? So in other words, we're crossing node boundaries with this 5 to 6 arrow. And then 6 is pointing to 7. Again, the left one points to the right. And the 7 is pointing to null because it is at the end of its level. Okay, so we're given this definition for node. It's just a bunch of public members and some constructors that allow us to populate nodes in different ways. And now we're going to try to do this. Now, remember, if you saw the first video, because we're doing this in Java, my claim is you don't want to use any additional libraries. You just don't want to fall into that trap. You want to use the standard libraries, even if you're doing it on your own computer, even if you're just a Maven wizard, or you use Gradle like, you know, every minute of every day you're defining a new Gradle project. It doesn't matter how experienced you are in these things, unless they're specifically asking to see your Maven chops. Don't do it. Right? What you want to do is try to keep this as focused and as narrow as possible. Again, you're trying to get engagement from the interviewer over the things the interviewer is specifically asking. Okay? So, because of that, let's take a step back. Remember, I feel like I have 4 steps to this process. Step number 1. In fact, I'm going to add them right here. Now, these are going to be the brief ones. Step number 1 is create the interface. Now, this does not mean we're in Java, and so interface means a thing in Java. Interface is a keyword in Java. I'm not suggesting that you create a Java interface. I'm saying they're asking you to do something, to perform something. A lot of times it'll be a function that they're asking you to write. Sometimes they're asking you for a data structure that you're trying to create. Sometimes they'll ask you, you're designing an API. Whatever it is that they're asking you to do, whatever the problem is specifically asking you to do, create the thing that is the request, right? Take that request that was given and translate the request, so not the implementation of it, but the thing they're asking you to do, turn that into something that is computer related, that is programming related. You want to translate the task into something that we operate in. And the reason that we're doing this is because that immediately gives a framework for the interviewer to comment and question. And that's, again, we're trying to drive that engagement with the interviewer. We want to give them an immediate way to interact at a code level with us. That's the point of these programming problems. We want to operate in code. A lot of times people will say, hey, make sure you ask questions and all that kind of stuff. My claim is you need to set some common context before a lot of those questions will come into play. Okay, so first one is create the interface, create the programming interface. The next one is create tests. Now, it's very natural if you're a test-driven kind of person. It's very natural to go create tests the way you would while you're working. And again, we're trying to drive a conversation, not necessarily illustrate the individual steps we would do when we were doing a process. What you're trying to do is say, I understand the problem. Here is what the problem is asking for. Here is a way someone might integrate or interact with the thing I'm creating. So this is what you want me to make. This is the way you want to interact with it. And it immediately lets you set up those questions and conversations and comments around code. And that's what you're trying to drive towards. So the reason for creating tests, even if you're not into test-driven development, is to say, I understand what you're asking me to do. Generally speaking, I would recommend creating 2 tests. You want to create one test that is sort of lightly complex, right? You want an interesting test, something that says, hey, I understand the problem. I understand some of the more compelling nuances, right? It's not about testing edge cases. It's about saying, hey, this is sort of I'm encapsulating the question and the things I see here. So for instance, in this particular problem, you wouldn't want to create a test case that's just 2 levels, because if it's just 2 levels, you won't get that moving from the left pointer or from the right pointer of a left parent to the left pointer of a right parent. Right, so you've got to go at least 3 levels to capture that test. But you also want to give yourself sort of a starting place, the easiest implementation, so that you can illustrate red-green, right? Again, the whole point is about having this conversation, engaging with them in a way that allows you to talk, and showing forward progress makes you look like a superstar. Making tests pass during your interview is awesome. So if you have the ability to do that, you want to do that. So again, I would say out of the gate, before we're doing any implementation at all, create a couple tests. Those tests are going to be a very natural place for you to ask questions about the problem, gain some more understanding. You can ask things like, hey, how nested can this get? Like how many levels are we talking here on this tree? When we start talking about the values, do I need to interact with the values at all? It looks like the values are just here as sort of placeholders. They're sort of irrelevant. Am I doing anything with the values before or after with all of this? Right? Having some sort of questions that you're asking once you're saying, hey, here's the problem you asked in computer language. Hey, here's how someone would interact with it and exercise it to see if I did it right in computer language. Then you can start asking about test cases, and the conversation is very natural. You're speaking to the code, not just answering hypotheticals in sort of vague terms. Okay. Number 3 is you want to quickly get into a red. So this is my claim. I realize this is not the way most people say it. A red refactor green loop. I do not think you should refactor after you have working code. The goal is to get working code. Once you get working code, you're done. Refactoring to make working code easier is great. Trying to squeeze the most perfection out of your working code is gross. I suggest not doing it. This is the way I approach problems, is red refactor green. A lot of people preach red green refactor. I think that's gross. I think it's wrong, but you do you. The whole point of the interview is to show off your skills. What I'm trying to say is quickly get into a loop where you can show forward progress. That's what you're trying to achieve here. Avoid over optimizations. Avoid too much, changing too many data types or creating too many crazy methods or going too far. Avoid perfection, because again, you're trying to keep them engaged, and what you're trying to achieve is the fastest path, well, not fastest, a fast path to working code. They want to ask you more questions. They can't really ask you more questions until you have something that works. Okay? So quickly get into that forward progress. Allow them to help steer you and guide you. If they tell you something an edge case isn't worth worrying about, don't worry about it. If they tell you an edge case is important, prioritize it. But the whole point is to engage them, keep them flowing in this thing. And a great way to do that is to continue this sort of forward progress where you see things fail, you see things pass. Okay. And the last one is be opinionated. I'm even going to go a step further. It's be clearly opinionated. So have preferences to the things you do. If you think every class member needs to be private, then come right out and say it. Hey, this isn't normally what I would do. I'm going to stick with it because it was in the given, but I am strongly opposed to public members. Here's why. Hey, it's cool to see public, but I would make them final. Something along those lines, right? Like, it's okay, be opinionated, say it. And the reason for this is, if you have working code and you were never opinionated, if you have working code, when they go back and talk to the hiring manager, all they're going to be able to say is, well, they implemented it. Your opinions and your beliefs, especially when you practice them, especially when you demonstrate them, what your beliefs and your opinions resonate with them, whether good or bad, they still resonate with them. and they'll have a thing to talk about with the hiring manager. And I know it's sort of scary to be like, well, but I don't want to say something that's going to offend you. I can almost guarantee that you won't be able to turn them off by saying intelligent things backed up with experience and data. If you think every member needs to be in a getter because you believe strongly in Java beans, that's going to be a little weird. I'm not going to lie. It's just going to be a little weird. If your justification for things is based on servlets, that's weird. But if it is, say it. Like, it's weird, but it's almost certainly not going to keep you from being hired. It is going to be a thing they can take back. It's going to be a thing they can talk about. They might even joke about it. But in other words, they might make fun of you, but you will have set yourself apart. It's okay to be opinionated. Try not to be wrong. If you have a controversial opinion, that's one thing. If you have a wrong opinion, that's another. Okay. So this is my claim. You want to do this in your interview. You want to do this in every programming problem, and you want to be quick and clear about these things. Okay. That was probably too long, but it's 15 minutes and we still haven't even started the problem. But let's dive in. So the first thing you'll see here is I'm using Java asserts because I don't want to bring in something like JUnit, but I still want to be able to sort of quickly test. Sun, in its infinite wisdom, decided that the only way you should ever be able to use an assert is by turning it on. So we have to come into our launch settings and turn on -EA means enable assertions. So when we come back in here and we run it, you'll see I now have this assert come up. Assert keyword, again, most people don't ever really run across it. This might even be a shock to some people that assert is even a keyword in Java. But what you do is assert some Boolean. If the Boolean is true, it'll just fall through. If the Boolean is false, it'll print out, or it'll throw an assertion error with whatever the message is after the colon. So we'll use this a little bit. I might even throw in an extra method. All right, so first thing we want to do, First thing we want to do is define our interface. So public propagate, or here, you know what we're going to do? We're going to populate next. And we're going to do that with some root node. We're going to wind up just returning the node. We'll populate these guys in place rather than creating a whole new tree. That may not be what they want. That would be a question worth asking. Nothing was really given about about the expectation here, except that we do say set the value of next in each node, as opposed to return a node, return a copy of the tree or something along those lines. So it's a question worth asking, but we're going to change it in place and then return the root. Excuse me. All right. So our two test cases that we're going to start off with. So this is our interface. This is what I mean by create an interface. We're just creating a function that is the thing we're being asked to do. The end result of this should be to populate all of the roots. It should be this output. Okay. Let's go do our tests. So the first test we want to do is the example that they gave. Whoops, I need new. In fact, right now let's come do a public static node n into val, return node val, and public static node n, node left, node right, and we're going to return new node val left, right. You may not want to do that. You may just want to do a bunch of news everywhere. We're going to probably be creating enough of these tests that yeah, it'll be here. 3, and then 3 is going to get 6, 7. Oh, except we need to populate next. So that's interesting. That's interesting. Yeah. The way I see to create the structure yeah, interesting. So the problem I'm running into now is how do we create the expectation of this? Does that make sense? How do we create this tree with all of the links, given that and the irony is the only way I see to do this easily yeah, the only way I see to do this easily is to yeah, the only way I see to do this easily is to actually perform the function in another way. But let's do it. This will make more sense. So node left, node right. Okay, so what we're going to do is node n equals new node val left right. We're going to return n, and then here what we're going to do is say left.next equals right, and left dot right dot next equals right dot left. So what we're doing is when we're adding when we're creating the node for 1, we're saying, hey, point 2 at 2's next should be 3. That's what the first line does. 2's next, so left's next should be right. Left's next should be right. But then we're doing is saying that left's right's next should be rights, lefts. rights, left. And then, so my claim is this is actually doing the algorithm, but it's doing it while we're instantiating the nodes. Okay? So what we're saying is, I'm going to pull this out so it's a little bit clearer. Node input equals this. Node output equals join 1, which is join 2, n 4, n 5, comma, join 3, n 6, comma, n 7. If that makes sense. So the claim is populating input should give output. Sorry. And then we're going to do node result equals populate next input. And our claim is result equals output. Now, and then if it doesn't, we want to do result dot toString. Now the problem here is, oh, right, new solution 2, not capital. All right, so the claim now is, and in fact, let's just go ahead and pull this out into something. We're going to call this public static Boolean void test node input node expected. So this should be expected. Assert result equals expected result toString. Yes, that all looks right. And so then we're going to test next input output. All right. And then we'll also do, in fact, let's do it before this. Test next n0, comma, n0. So so yeah, our first test, we're just going to go with an empty input to see if that works. All right, so because all we're doing is just returning the root, well, it should fail on the first one. See if you can guess why. We failed on line 78. Yeah, so we failed on the first one. You'll notice that our toString isn't very useful. And it failed because our equals is the default equals. So we need to come in here and do equals. It doesn't just populate it. That's fine. Or you know what? Let's not even do that. Instance of node Man, if object not object instance of node return false. Return n.val equals and object dot equals this dot left comma n dot left and object equals wait oh being dumb objects equals n.right equals next and just because I am being a little OCD right at the moment, we're going to do it that way. All right, is it going to collapse them back? No, it didn't. Cool. All right, so now we have our equals. Let's go ahead and do our toString. And for our toString, we will return, what do we want to return? Let's return it as, hey, isn't there a new string literal? New. It's probably not that new. Java string. String interpolation, is that right? Format, string builder, message format, string templates, that's what it was. STR template processor, huh? It's worth noting since string template is a preview feature in JDK 21. Okay, well, so I don't have that because I'm pretty sure I'm in 17. All right. So we're going to return this .val. Oh, I know. So if this .next. Well, wait. Okay. So the first thing is sorry, that's just sloppy. Integer dot toString. String result equals if this dot left, then we know we have a left right. Not equal null. Then results plus equals. We're going to do that plus this dot left plus, let's do a pipe, this dot right, and we're not checking whether left and right, or whether right exists also, because right has to exist in this particular problem. And we'll do if this dot next is not equal null, then result plus equal we'll do that with a little arrow plus this dot next dot val. Else result plus equal. No, you know what? That'll be fine. That'll be fine. Return result. All right. So hopefully adding in that equals will just pass this first one and we'll get an interesting printout on the second one. Let's try it. Cannot assign field next because left.right is null. That makes sense. So let's go fix that. That would be here. So if left.right not equal null, sure, that makes sense. So now let's run it again. And we can see that we output, oh, and in fact, let's make our plus is not expected. There we go. Now we can see if our toString is doing what we wanted it to do. That's a little bit harder to read than I wanted it to be, isn't it? I think it's working the way we want. But let's switch the order on this toString to make it a little bit easier for us to understand what's happening. I don't want to ask Copilot anything. There we go. So now what we're expecting is to see the next pointer up front. Oh, that's interesting. Yeah, oh, right. So 1 is pointing to null. That's what we set up here. 1 is pointed at null. 2 should be pointed at 3. And 3 should be pointed... Oh, wait. Yeah, sorry. It's just in the terminal, so we can look at here. 2 is pointed to 3. 4 is pointed to 5. 5 is pointed to 6. 3 is pointed to null. It's not pointing to anything. 6 is pointed to 7, and 7 is pointed to null. Okay, so we're pretty confident we're actually doing, our test case is doing the algorithm. So we've technically solved the problem just by constructing our test case. But the problem was asking us to set it, not to create a tree with the right result. Because we're not, maybe it's obvious, but we're not actually doing the algorithm in this line because we haven't been given the root of a tree. But we understand almost exactly what populate next needs to do for a particular node. In other words, we should go to each node and do, wait, where'd I put it? We should go to each node and do this. Does that make sense? So each node in this route, we just visit each one of them, and we want to set these two properties because we're pretty confident it's working the way we want it to. We want to set those two properties. Whoops. Not sure what I hit to lose my... There we go. But we want to set those two properties. I'm going to scooch that over a little bit. There we go. On this end. So we're going to do n. And n. And honestly, I would love to put this in the node itself. We may talk about that more here in a little bit. Return n. Now this is only doing one node, so we need to populate. Oh, yeah, we're not using, yeah. So populate next n.left populate next n.right, and return that. Now, you might not be comfortable with using recursion this way. In other words, we're doing the exact same thing we did down here. We need to add in an if n.left does not equal null. We don't want to set next if it doesn't exist. It may be uncomfortable doing recursion this way, but let's go ahead and run it, see if we pass our tests. Cannot read field right because n.left is null. Oh, right. This should be in this. Should be in this one. So in other words, there's no point in checking. You need left to not be null for there to be a right. So that makes sense. And in fact, these populates only make sense inside of here as well. So in other words, you don't need to check left and right if left was null. So let's try that. And sure enough, that worked. So we are getting this, for this input, we are getting this output. We printed it out and saw that it was doing the joins the way we expected to. It's different than the input. You'll see here the input is just divided by pipes and square brackets. So we're pretty confident we have now done the thing that we were asked to do. My claim then, or actually, you know what? It's not even about claim necessarily. Let's scooch back over here. So LeetCode had a couple of follow-ups. So we're gonna pretend that one of these the first follow-up was you may only use constant extra space. So then the question is, does this use this approach? Does this use constant extra space? And the answer is technically no, because of the we're using stack space for this recursive solution, right? So let's ask instead: is there a way for us to do this problem with constant extra space without recursion? Does that make sense? We're gonna do this operation without recursion, but without having any sort of a stack. So almost any recursion can be sort of unwound into a stack. So in other words, we could just push n.left and n.right into a stack and just have a loop here. That's here. I'll do it. Why not? List node working equals new list.of n. You know what? If I remember right, this actually won't play nicely. So let's do this as new array linked list. Sorry, I'm doing it backwards this way. Add all I'm missing imports. And then we're going to do working.add n while working.empty is empty. While it's not empty, Control X, V. We're going to pull out n equals working.pop. What is it? remove 0. Node n. Working dot add n.left. Working n.right. Return root. All right, let's test this, see if this works. Yep, sure enough. So again, any recursion can get squished back down into just working a stack, right? Because that's all that was happening. So is a recursive approach using constant space? No. Is that using constant heap space, which is almost certainly the question that's really being asked? Yes. Right? Because stack and heap are different. We're not using dynamic memory. We're not using dynamically allocated memory. We're using the space on the stack to manage it. Is that cheating with that question? It's sort of, I would say it's open to interpretation, but the point is we can do it. We understand how to do it, right? Because we wrote this method, which didn't need any extra storage. So in other words, the whole question is, can we walk this stack in constant space? Actually, do I know how to walk that stack in constant space? I mean, I know how to walk the stack in constant space if we add a parent to a node so that we know how to work back up the tree. I'm not sure. Yeah, I'm not sure if I understand how to do this in constant space. What a weird question. So I will say in LeetCode, they say the recursive approach is fine. You can assume implicit stack space does not count as extra space for this problem. I think that's a little cheating. I personally, I would say the recursive solution is not constant space. So can you do this in constant extra space? I don't think you can. Because I think breadth first and can you cheat with the pointer? Can you get away with it with next? You might be able to. Oh, that's fun. We have to try it. That's fun. So here's the point of this. While we're walking through and populating these things, so remember, when we process one, we're going to set its children are going to get their next pointer set. And their children's their grandchildren are going to get joined across the boundary. Okay? So in other words, when we process node 1, we're going to do this next as well as this next. We haven't sucked up any extra storage. Right? When we're processing this node, we look at this one and then this one. Then we're going to process node 2. And we're going to forget totally about node 1. Node 1's gone. We're throwing it away. We're going to go process node 2. When we process node 2, we're going to set its left child to point to its right node. So we're going to do this arrow. Remember, this arrow already is set. Now we're going to add in this arrow when we're processing 2. If 2 had grandkids, we would be doing the arrow in between 4's right child and 5's left child. So bizarre, right? So if there was another row here, we would be setting that arrow down below there. But then from 2, next points to 3. Oh, but we don't have a way to go from 3 to 4. Yeah, okay. We don't have a way to go from 3 to 4. Oh, yeah, that's our constant space. That's our constant space. So we have to remember the first child of the next row. Does that make sense? We have to remember the first child of the next row so that when we see a null on our row, on our level, we know what the next one to do is, which will be the next child on the next row. And when we do the next child on the next row, yeah, crazy. Okay, let's see if we can make this work. Okay. So I'm going to create a method that does this. Work so that we don't lose it. Public Boolean connect n. So if it doesn't have children, we're going to return false. Oops. Shift down. Okay. So all that connect is going to do is return true if it's, so it will return true if it's a leaf, or I'm sorry, true if it's a parent, if it has children, and false if it's a leaf. And when we're done, it will have done the 2 arrows we need it to do. Okay, so now we have connect. I'm going to come down here and say if connect n, that's when we want to add in. So if we knew it was a leaf or not. Part of me even wants to break that out. Public Boolean, just to be, is leaf node n. Again, this is the sort of thing I would put on the this is return that it has no children, is leaf. And so now I'm actually going to pull this just to make everything clear. If it's not a leaf, we're going to connect in, do all that. This one is staying like that, and then if is leaf and n.left. And really, it's if it's not a leaf, we want to do its join here. And now we're not going to have this. This is going to be a void. This is going to be a not. This will be an extra brace, and that should make this more clear about what's happening here. If n isn't a leaf, we want to work on its left child and connect it to its right. If its left child wasn't a leaf, we want to connect the right of our left child the right grandchild of our left child to the left grandchild of our right child. That all makes sense. Okay. And then down here we're saying if it's not a leaf, connect it. And then add the left, add the right. Okay. And again, these things that are operations on the node itself Personally, I would have rather had these two in the node, but we were given this node class as though it was extra. Although I did add an equals and a toString. We'll move on. No, you know what? I can't help it. We're going to do it. Boop. Boop. Boolean isLeaf. Return. isLeaf. Connect. Instead of ends, they're all this is. And honestly, I mean, this is violating law of Demeter. I don't really care about law of Demeter as much as some people do. I do think this is probably getting a little egregious, but we'll move on. Law of Demeter, just to have said it, you want an object to be responsible for its own changes. So here we're changing a next pointer of a grandchild. What should happen instead is that you tell the left node, hey, here's your new right. And then you tell the left node to operate against that right, to sort of do the inside joins or the cross join. So, yeah, this it's a tiny bit egregious, but for right now, and in an interview, I don't think it's really horrible. You're still capturing the right thing. Okay, so then we come down here, and that means that what's really happening is we're asking if n is not a leaf, then connect it. And then add its children to our working list. So we've made a bunch of changes. Let's go ahead and just run it again just to make sure everything's still sane. It is. Now what we want to do is get rid of this working altogether, which is crazy. I'm going to say what we want to do is populate level. Oh, but that's still going to be recursive. Yeah, okay, populate next. Oof. Okay, so what we want to do is say node level start equals root, node working equals null. Wow. Level start is not null. Working equals level start, while working is not null. Yeah, working equals level start, and level start equals working dot left. Right, okay. So maybe this doesn't make sense. Let's just talk about it real quick. What we're basically saying is we need to remember when we were going through our thoughts earlier, we were saying, hey, we need to remember who the next guy down is whenever we process this level. And so that means when we start processing this level, the next guy down is the left of whoever we're starting with. So when we start processing a new level, that's what this where we go. That's what this loop is. We're going to, while we have more levels to process, because we have a level start that isn't null, we're going to start the new level. So our working guy is going to be this first level. And then we're going to immediately set the level start of the next level to that guy's left node. And then while working is not null, if working dot is leaf, working dot connect. And then leaves can have nexts. So working equals working dot next. Oof. How crazy is that? I think that's right. No kidding. Well, there you go. That is the non-recursive, or a constant extra space solution. Crazy that that works. But there you go. Okay. We've hit the hour mark. I hope that was helpful. Again, the point of this is to see both how to practice using this, but then also you're practicing using this so that you can use this. Hopefully, while we were going through this, you were responding to me being an idiot in different places, asking questions I wasn't sure about. You would have had comments. If this was a conversation between the two of us, you would have potentially had things to say the whole time. Hopefully this was that kind of engaging so that you understand and see, if you were my interviewer, that's how you would interview me. And it would be very natural to break in and jump in and say, hey, wait, no, when you're doing this, that isn't going to work. Right? If I get derailed and I'm going down the wrong path, you can say, hey, wait, no, that's not the right path. Let's talk about this. Right? And get me back on track. Make sense? Cool. I hope you enjoyed it. I hope to do more of these. Yeah. I'll let you know. Thanks.